we'll consider the concept of the node voltage analysis. So where we are going to apply the Kirchhoff's current law we are going to apply. So this Kirchhoff's current law will be helpful. So we are going to assume that the current entering the node is equal to the current leaving the node. So we are going to apply the concept of the Kirchhoff's current law we are going to apply in order to evaluate that network here. So by using the node voltage analysis, we can able to obtain the node voltages such as the V1, V2 or V3. So whenever the circuit is given, we need to identify the nodes where the circuit elements are connected, and the corresponding voltages we need to identify as the V1, V2, V3, and so on, V4 we need to identify, and along with the mini source will be there. So among the nodes, one of the nodes where the maximum circuit elements are connected, we are going to consider that as the reference node we are going to consider, and we are going to denote that one with the datum node or the reference node, and that voltage we are going to make equal to the 0 volts we are going to make here. When you are applying the KCL or the node voltage analysis, we are going to apply that concept here. And also, we are going to make the certain assumptions we are going to make for this one. We are going to make the certain assumptions you are going to make. That is, for all the nodes, we are going to assume that the current is the all the nodes, the current are leaving in the all the nodes you are going to assume here. At the respective node, all the currents are leaving. We are going to make that assumption here, and that one you are going to take with the positive polarity. So, but if any current is entering the node, we are going to take that one with the negative polarity. We are going to make as we are going to assume that one. So the first assumption is we are going to assume that at the particular node, all the currents are leaving, and that one you are going to take with the positive sign you are going to take. And if any current entering the node, we are going to take that one with the negative sign we are going to take here. And this is assumed that the current is leaving, and this is current leaving here, and also the current is leaving. And a similar way, we are going to assume the same assumption. And when you are applying the KCL at the particular node, we are going to assume that. So to consider, and if any voltage source is there, that the difference will be taken and divided by the resistance as per the Ohm's law, that is I is equal to V by R. We are going to apply that concept, and we'll find out the corresponding values we are going to find out here. So here that's the assumption you're going to make. The first assumption is the currents at the node, all the currents are leaving the node. Any current is entering the node, we are going to assume with the negative sign, and one of the node will be taken as a reference node with the zero potential. And when you are applying the KVL, we are going to apply it on particular point, and we'll take the difference of the current value we are going to find out. The current is nothing but, as per the Kirchhoff's current law, the sum of algebraic sum of the current entering the node is equal to the current leaving the node, and that value is equal to the 0 we are going to assume here. So now let us apply the KCL. We are going to apply the KCL at the node V1. At node V1 we are going to apply. So at the node V1, the current we are going to assume as leaving the node. So it is V1 minus E1 divided by the Z1 we are going to assume. So it is V1 minus E1 divided by Z1 plus V1 minus 0 divided by Z2 we are going to assume. So it is V1 minus 0. The 0 is a reference voltage divided by the Z2 plus V1 minus V2 divided by Z3. V1 minus V2 divided by the ZT3. So this is equal to 0 we are going to assume. So since for this node, none of the other nodes are connected, we're going to make that as a 0 here. So let us simplify this one. So let us take the V1 term separate and V2 term separate. Let us take here. So it is V1 is equal to so it is we are having 1 by Z1 plus 1 by Z2 plus 1 by Z3 is there. And V3, V2, we are with the negative sign. So it is 1 by Z3. So this is equal to the value which is equal to the E1 we have. So we can call this as the equation number 1. We can call here. So call this as the equation number 1. We can call here. This is the equation 1. This is the equation 1 we call here. So now similarly, let us apply the KVL for the Kirchhoff's current law for the node 2 we are going to apply. So we'll apply the KCL at the node 2. So apply KCL at node 2. So all the nodes we are going to apply the KCL we are going to apply for all the nodes, and we'll find out the respective node voltage expressions we'll got in terms of the 1, 2, 3. So here at the node V2, so it is we are going to again assume that the currents, all the currents are leaving the node. So it's a V2 minus V1 divided by Z3 and V2 minus V4 divided by Z4. and V2 minus V3 divided by Z5 we'll assume here. So it is V2 minus V1 divided by Z3 plus V2 minus 0 divided by Z4 plus V2 minus V3 divided by Z5 is equal to 0. So we'll simplify this one. So what we can do is, so for the node V1, the value is minus 1 by Z3, plus for the node V2, the voltage source are, so 1 by Z3, 1 by Z4, 1 by Z5, 1 by Z5. So these are the values for the node V3, node V2. So this is 1 by Z5. And for the node V3, we have from the expression, so it is V3 into minus 1 by Z5. So this is equal to the 0. Let us call this as equation number 2 here. Let us call this as equation number 2 here. And similarly, we'll apply the KCL for the node 3 will apply. So we'll apply the KCL for the node 3. We'll apply the KCL for the node 3 here. So in the node 3 we have, this is a circuit element is there. So we are going to again assume that all the currents are leaving the node, we are going to assume. So it is V3 minus E2 divided by Z7 and V3 minus 0 divided by Z6 and V3 minus V2 divided by the Z5 is equal to 0. So we'll take that one. So it is V3 minus E3 divided by the value for the impedance is it's Z7. It's a Z7. Again, we have so V3 minus 0 divided by Z6. V3 minus 0 divided by Z6 plus V3 minus V2 divided by Z5. V3 minus V2 divided by Z5. So this is equal to 0. Now let us simplify this one. So for the V2, we'll take here. So V is equal to minus 1 divided by Z5 plus V3 will take 1 divided by Z6 plus 1 divided by Z5 plus 1 divided by Z7. So this is equal to the, so we have a E3 by Z7 we have here. So here I'll call this as equation number 3 here.